4.1, the vertex of a quadratic function. So the goal here is to compare the standard and the vertex forms of a quadratic function. So let's try and remind ourselves, what are the three different forms of a quadratic function? Well, we have the vertex form, and that looks like this: f of x equals a times x minus h squared plus k, where h and k give you your vertex, and a will indicate to you your direction of opening, and from the vertex we can get our axis of symmetry and optimal value. Then we have the standard form. So the standard form looks like this: f of x equals ax squared plus bx plus c. And from the standard form, we can get the direction of opening. And through some other methods, we can also find the axis of symmetry. And the axis of symmetry can be obtainable by using this formula: x equals negative b over 2, assuming if a is equal to 1. And we also have the factored form. And the factored form looks like this: f of x equals a times x minus r times x minus s. And the factored form is very useful for us when trying to determine the x-intercepts. So let's see if we can complete the following table. And below we have a bunch of equations in vertex form, and our particular interest is in the vertex form in this particular chapter. So let's try and recall what some of these functions tell us. So if I look at the first one, so we have equation 3 times x minus 2 squared plus 1. Well, the vertex comes from h and k, and h and k are these two values right here. So you have an h value of 2 and a k value of 1. The axis of symmetry is related to the x value of our vertex, so that's going to be x equals 2. And we have a minimum value because our a value is positive. It's positive, that means the graph opens up. And if it opens up, then of course the graph will have a minimum value. And we don't have any x-intercepts because we have a and k being the same signs. So our minimum value is above the x-axis, and so our graph will never cross the x-axis if it opens up. And then our domain and range are given as follows. So every real number exists for x, as it does for all the parabolas and that we study in this course. And the range is a y value greater than or equal to 1. And again, the range comes from our value of k and the value of a. So if I look at the next one, 1/2 x squared minus 5. So we see here we have no brackets. And when we have no brackets, it means the h value is 0. So in our vertex, we're going to say the vertex is 0, comma, and the k value is negative 5. So I will say negative 5 for my y value. Continuing, the axis of symmetry is x equals 0 because the x value of our vertex is 0. We have a value that's positive, so it's going to open up. So we are going to have a minimum. And because our k value is negative, that means we are going to be below the x-axis. So if we are below the x-axis and the graph opens up, then we are going to cross the x-axis 2 times. So we will have 2 x-intercepts. Okay, and so this is always indicated to us by a and k being opposite signs. And domain and range, again, domain is going to be x as every real number, and the range will be y as every real number, such that y is going to be greater than or equal to negative 5. Okay. So I'd like you to try the other two on your own, see if you can recall how to find these different characteristics. So pause the video, write them out, and then I will display the answer. Okay, so hopefully you've been able to find the answers on your own. Here they are, just so you can check your work. So this one here is 4 over 8 for the vertex. We have an axis of symmetry is x equals 4. And we have a maximum. Here we have 2 x-intercepts. Again, a and k are different signs. And domain and range, x is the element of all real numbers, and the range is y is the element of all real numbers, such that y is less than or equal to 8. For the last one, we have a vertex of -5 and 0, axis of symmetry of -5. We have a maximum value as our graph opens down, and we have one x-intercept because the y value of a vertex is 0, so we are going to be on the uh, x-axis there, like this, rather over here on this side. Okay, and our domain and range will be x epsilon r and y epsilon r, such that y is going to be less than or equal to 0. Okay, so moving on, we have just reviewed some of the things that you can, characteristics of some vertex form functions that you can find. Let's move on to some things that we need to know how to do. So you may be asked to turn a equation in vertex form into an equation in standard form. And to do this, you're going to do the same thing like we did with the factored form equations. We would choose to expand those and simplify. So we're going to expand and simplify. Okay, so let's look at what we have here. So when I expand this, I'm going to read this as f of x equals 3 times x minus 2, and because it's squared, I'll multiply it by itself again, x minus 2, plus 1. So I'm going to expand these two brackets using the distributive property. So x times x is going to give me x squared, and I have minus 2x, and then minus 2 and minus 2 gives me positive 4 when I multiply them. Put this in brackets because you still have to distribute that 3, and then outside I have plus 1, and then we carry on with the next step. So if I distribute 3, I'll have 3x squared. I can combine these two like terms, minus 2 and minus 4, to give me minus 4, and minus 4 times 3 will give me minus 12, so minus 12x, and then 4 times 3 is plus 12. Outside I have plus 1. And if I simplify one more time, keep these terms here, 3x squared minus 12x, and 12 plus 1 give me 13. And so there I have my equation now in standard form. If we look at the next example, similarly, you can do the same thing. -3 stays outside, create your brackets. What we're going to be doing is x plus 5 times x plus 5. We're going to expand this using the distributive property. So you just multiply each term in the first bracket with each term in the second bracket. So what we're going to have is x times x, which is x squared, x times 5, which is 5x, again another 5x, and then 5 times 5 is 25. Then we distribute the -3 with all of our terms, so when you have -3x squared, 5x and 5x can be combined together to give you 10x. When I multiply that with -3, I get minus 30x, and then 25 times 3 is minus 75. And there you have, again, your equation in standard form. Okay, now, a similar problem like we did in the previous chapter, we were asked to write equations. We're going to write the equation of a quadratic function with a vertex of -3 and -6 that passes through the point -1 and 2, first in vertex form and then in standard form. Okay, so by being given the vertex, it cuts down a lot of the work that we have to do. So it makes us much more able to write the vertex form much more easily. So we're going to say here vertex form. Okay, so we're going to write out the vertex form generally. So f of x is equal to a times x minus h squared plus k. And then I'm going to replace my h and k with the actual values for the vertex. So I'm going to use that vertex, -3 and -6. And I'm going to write here f of x equals a times x. So x minus -3 becomes x plus 3 squared. And your k value is -6, so -6 goes out there. So our vertex form is actually almost complete, except we're missing the a value. So to find the a value, I need to solve this equation for a, and to solve this equation, even before I can solve it, I need to find values of x and y that I can use to substitute. So what point can I use? Well, I'm going to use this point right here, -1 and 2, as my substitution point. So I'm going to write here subpoint -1 and 2 to find a. So when I do that, I'm going to write 2 equals a times -1 plus 3 squared minus 6. Okay, so now when I add these two together, inside my bracket, -1 plus 3, I'll get a positive 2 squared minus 6. But really what I'm going to be doing here is just solving for a, because a is now the only unknown value. Make sure you follow your rules for BEDMAS when doing this. So 2 squared will be evaluated to become 4, so we have 4a minus 6. And then the goal is to isolate a, so I'm going to do reverse order operations here. So minus 6, I'll add 6 to both sides. So on the right side, the 6 goes away. I'm left with 4a. On the left side, I have 2 plus 6, which is 8. And then if I want to get rid of the 4, I'll divide both sides by 4. So 8 divided by 4 equals 4 divided by 4, which just gives me a. And then the last step is 8 divided by 4 equals 2. So my a value turns out to be 2. And that's what I'm going to use to complete the equation. So my equation, therefore, is f of x equals 2 times x plus 3 squared minus 6. Now, if I wanted to write this equation in standard form, I can take my vertex form and expand it. So if I take my vertex form, f of x equals 2 times x plus 3 squared minus 6. Let's write here standard form. Just expand it. So I'm going to say 2. So x plus 3 squared can be written as x plus 3 times x plus 3 minus 6 goes outside. So what I wanted you to do is distributive property using for these two brackets. So I'm going to write 2 times x is x squared, 3 times x is 3x, 3 times this x over here is another 3x, and then 3 times 3 is 9. Close the bracket, minus 6. Now I just distribute the 2 with what I have in here. 2 is being multiplied with my product here, so I'm going to distribute that 2. So 2x squared, 3x plus 3x is 6x. When I multiply that with the 2 I have here, will become 12x. And 2 times 9 is 18. Don't forget you have a minus 6 outside. You're not going to multiply with that 2 because it's not being multiplied with the 2, it's being subtracted. So let's leave it as a 6. Then you collect some like terms here, so we have 2x squared, 12x, and 18 minus 6 is plus 12. And there you have it. Last example here. So let's write this function in vertex form. So what we have here is a factored form. So to get vertex form, we still need an hk and an h value and a k value. Okay. Now we do have an a value. There's an invisible a here with a equals 1. So we're going to use that for our a value. Okay, but the vertex form, we're going to say needs h and it needs k. Okay. Well, our h value is the same thing as the axis of symmetry, and the k value is the same thing as our optimal value. So I can use the factored form to help me find my axis of symmetry. So remember that if we want to find our roots, we set our function equal to 0. Okay, so we have x, 0 equals x minus 3 and x plus 9. Okay, and so from this I can say my roots are positive 3 and negative 9, because these are the two values of x will give me 0. So if I was interested in finding my axis of symmetry, I add my two roots together, 3 plus negative 9, and I divide by 2. When I do that, I get negative 6 over 2, or simplified to negative 3. So there's my axis of symmetry. Therefore, I can say h equals negative 3. And if I wanted to find my optimal value, I'm going to substitute that value back into my equation. So I'm going to say f of negative 3 equals negative 3 minus 3 and negative 3 plus 9. This will correspond to the y value at x equals negative 3. So negative 3 minus 3 is negative 6. Negative 3 plus 9 is positive 6. So my optimal value is going to be negative 36. So k equals negative 36. And therefore, I can now say my function in vertex form is equal to x plus 3 squared, because remember it's x minus h, so x minus negative 3 becomes x plus 3, and then my k value is minus 36. And there you have it.